All right, so we're going to move on to lesson 7.6, which is still talking about this idea of a sampling distribution, but we're dealing with a different type of data. Specifically, we're going to talk about categorical data, which is when we are finding the proportion of something. So as a reminder, remember that a sampling distribution is really just a collection of sample statistics. So last class, in the last lesson, we talked more about sample means. So that was numerical data. We found the mean and the average of things. In this lesson, we'll look at sample proportions. So when we have categorical data. So we're going to jump into a little applet where we'll do some coin flipping to explore what happens when we take lots and lots of samples and find the proportion of flipping heads. So I'm going to go over to that little applet. So on this one, I have my setup here. I'm going to leave my probability of flipping heads at 0.5 because that makes sense. That's pretty much the probability of flipping heads on a coin. And I'm going to set my number of tosses to 10. So I'm going to have 10 coins. That's my sample size. And repetitions just means how many times do I want to take the sample. And I'll just do one for now. So I'm going to click, I'm actually going to change this to proportions because we are going to be talking about proportions in this sample or in this lesson. And then I'm going to say draw samples. So it's basically flipping 10 coins and then it's going to give me the results. And in this test, I got 6 heads and I got 4 tails. So down here on my graph, I now have a little dot above the 0.6 because in this repetition, in this trial, I had 60% heads and 40% tails. So 60% heads, that's what we marked here. If I take another sample, I'm not necessarily going to get the exact same result. So in this sample, I got 4 heads and 6 tails. So I got 40% heads on this one. So notice that on my graph down here, there's now a dot above 0.4 for 40%. Every time I take a sample or flip 10 coins, I might get a slightly different result. And this graph down here is keeping track of all of those results in terms of what proportion of heads I'm getting. So now is where I'm going to speed things up. I'm going to take 10,000 repetitions or samples of this same thing. So when I click draw samples, this is the last attempt that we just did, or the last repetition. And now we have this graph down here that is showing us all the different proportions for all of those samples that I just took. And you'll notice that the most common was right here in the middle at 0.5. That was the most common result, which means most of the time we had 5 heads and 5 tails. But you'll notice that it's not perfect. We had definitely some situations where it was on either side. I even had a couple times down here where I only had 10% heads. And there were even a couple up here where I had 90% heads. So there's definitely some variation. This right here, this graph, is another sampling distribution. It's a collection of sample proportions. Okay, so if I were to change my probability, or if I were to change my sample size, that's where things might change in terms of my sampling distribution. Both of those things, the probability of flipping heads and the number of times that I toss a coin, the number of coins that I have, are both going to affect how this graph looks. So just to explore that a little bit, I'm going to click this little box that says show sliders. Right now I have a sample size of 10 and I have a probability of 0.5. So first I want to look at what happens when I change sample size. So if I were to decrease sample size, so make it go down, okay, it's kind of hard to tell, but it did spread out a little bit. So instead of going from like 0.1 to 0.9, I'm now going from 0 to 1. So decreasing the sample size spread out that graph a little bit. If I go in the other direction, if I increase my sample size, and again, it's a little hard to tell because this graph kind of adjusts, but notice that we're now going from like 0.2 to 0.75. If I increase it even more, I'm now going from 0.3 to 0.68. So we are getting a little bit narrower the bigger my sample gets. If I get all the way up to 100, my sample goes, or my graph goes from like 0.36 to 0.64. So it's definitely narrowed quite a bit. So increasing sample size, a smaller sample makes the graph more spread out, and a larger sample makes the graph less spread out. So that's actually the same as something we noticed in the last lesson. When we increase sample size, the spread of the graph goes down or gets narrower. When we decrease sample size, our spread, our standard deviation, gets bigger. So that is something that's the same as what we learned in the last lesson. So now I'm going to turn this back to what it was before, 10 and 0.5. Now what I want to do is look at what happens when I change the probability, because that's another thing that could have an effect on the way that my graph looks. So right now it's at 0.5. We have a 50% chance of heads. I'm actually going to hide the coins because they'll go crazy in a minute. And I'm just going to move this back and forth. So let's say we had a weird trick coin somehow that only had a 10% chance of landing on heads. That's close to 10%. Right, so I noticed that my graph looks a lot different. It's now a completely different shape, right? And it is a little bit less spread out as well, but mainly I'm noticing that difference in the shape. When we were back at 0.5, that graph had a shape that we would call roughly normal. It's unimodal, it's got one peak in the middle, it's pretty symmetric, it's pretty normal. But when I decrease my probability down to about 0.1, or even below that, I end up with a graph that's a lot more skewed, right? We kind of notice that the peak, the whole graph kind of moves to the left, and it's skewed to the right. Remember, the skew direction is where the lower values are. So skewed to the right because everything moved to the left. If I change my probability to way up here, maybe at 0.9, the opposite happens. Everything kind of moved over towards the right, and now it looks more skewed to the left. So probability does have a big impact on the shape of the graph. The other thing I want you to notice is if I have a bigger sample size, right, moving my graph left and right doesn't change the shape quite as much. It's lagging a bit, so it's hard to tell. It does change it a little bit, but when I have a really big sample size, the shape doesn't change quite as dramatically. It's more likely to look roughly normal no matter where my probability is. So that's something interesting to note as well. Both of those things, N, which is sample size, and P, which is the probability, are going to have an effect on the shape of that graph. All right, so again, kind of things we learned here. When we increase and decrease the probability, that changes the shape of the graph. Smaller probabilities kind of move everything to the left, which tends to make the graph look more skewed right. And a larger probability tends to move everything to the right, which makes the graph look more skewed left. Remember the skew direction. Sometimes I know a lot of you guys will get that backwards because it feels opposite to you. So the skew direction is where the lower bars are. And then when our sample size is really big, right, the probability doesn't seem to have much of an effect on the shape. But the graphs overall are still not very spread out compared to when they had a smaller sample size. So that's still true. So let's put that all together with a rule. So these are the rules for our sample proportions graphs. So when we take many, many samples of the same size, the distribution of sample proportions, our sampling distribution for sample proportions, will be approximately normal as long as NP and N times 1 minus P are both greater than or equal to 10. So that seems like a big leap. But basically what we discovered, or what I just showed you when we kind of moved these little sliders around, is that both N and P kind of have an effect on the shape of the graph. We also noticed that with a larger sample size, the probability didn't have as much of an effect. So other people smarter than me who have been around for much longer in the statistics world did a lot of trial and error and figured out that this little rule works. As long as N times P and N times 1 minus P were both at least 10, then the graph looked approximately normal. So that is the rule that we're going to use, and I will show you how we actually use that rule in an example in a moment. So that's the first thing. The second thing is that the mean, the center of our sampling distribution graph, is always going to end up being the same as whatever P was, whatever the probability of success was in your problem, that's going to be the center or the mean of our graph. And then the third thing is we noticed that the standard deviation or the spread of the graph, how wide or narrow it was, that standard deviation decreases as your sample size increases. So the sample size goes up, the spread or the wideness of the graph goes down, and vice versa. And then again, like I said, smarter statisticians, people who have been around this stuff for ages and did a lot of trial and error, kind of figured out what that formula is for our standard error based on what we know about P and N. Okay. So now let's look at some examples. So our first type of example is really just thinking more about the shape. So again, our main rule there is that if N times P and N times 1 minus P are both at least 10, the graph should look roughly normal. If they're not both at least 10, we have to do a little bit of extra thinking and maybe some trial and error, but that is our main rule. So part A, we have an N of 20. We're trying to determine the shape of the distribution based on these values. So N is 20, P is 0.3. So let's check our rule. N times P would be 20 times 0.3, which is 6. 6 is not bigger than 10, so we know already that it's not roughly normal. So what is it? Well, it's probably skewed. To determine which direction it's skewed, remember if P is lower, if it's on the lower side of things, if it's, in the earlier probabilities, then that means everything moved to the left on the graph, which means it's skewed to the right. So P is on the smaller side, the graph will likely be skewed right. Remember, the skew direction is always kind of on the other side. It's where the lower bars are. So it may seem backwards. For part B, N is 50, P is 0.4. So let's check our rule first. N times P is 50 times 0.4, which is 20. So far, so good. That's greater than or equal to 10. But we also need to check N times 1 minus P. So N times 1 minus P, 50 times 0.6. 1 minus 0.4 is 0.6, which comes out to 30. That is also greater than or equal to 10. So since both of those are at least 10, we know that this graph would look roughly normal. Part C, 50 and 0.9. So N times P, 50 times 0.9 is 45, bigger than 10. N times 1 minus P, 50 times 0.1 is 5. So it's not bigger than 10, which means this one is not normal. We know it's skewed probably. Which direction is it skewed? Well, again, P is on the higher side, right? Which means everything moved to the right in our graph, which means it's probably skewed to the left. For part D, N is 100, P is 0.9. N times P, 100 times 0.9 is 90. N times 1 minus P, 100 times 0.1 is 10. Both of those are greater than or equal to 10. 10 counts because it can be equal to 10. So that one would probably look roughly normal. So that's how we can do some stuff on shape. Example 2, we're going to actually apply this to what we learned in the last unit. So Harley-Davidson motorcycles make up 14% of all the motorcycles registered in the US. So the first thing I'm going to ask is if we took many, many samples of 50 motorcycles, would the distribution be roughly normal? So that would be using that rule we just talked about. In that case, 50, which is N, times 0.14, which is P, is 7, which is less than 10. So that would not be roughly normal. And again, because P, 0.14, is on the lower side, it would probably be skewed to the right. But what if we took, on the second part, what if we took samples of 200 motorcycles? So now my sample size is 200. So N times P, 200 times 0.14 is 28. N times 1 minus P, so 200 times 0.86. 1 minus 0.14 is 0.86, is 172. Since both of those are greater than 10, or at least 10, then we do know that this one is roughly normal. So voila, with 200 motorcycles as my sample size, that one will look roughly normal. What is the mean of the distribution? Right, remember our rule was that the mean is going to be equal to the probability of success in that problem. So in this example, our probability of success is 14% or 0.14. So the mean is 0.14. That basically means on this normal model graph, right there in the middle is our mean of 0.14. So this graph is going to give us the proportions of Harley-Davidsons we would get in all of these samples. For the standard deviation, right, that's where we have the formula. So square root of p times 1 minus p over n. And do square root of 0.14 times 1 minus 0.14 divided by 200. Be careful about order of operations on ones like this in your calculator. All right, we would do the top part of the fraction first, so 0.14 times 1 minus 0.14, and then divide by 200, and then take the square root at the very end. We're going to get something around 0.025. It keeps going after that, but I rounded it. Right? Where the standard deviation comes in, just like we learned in the last unit, just like we learned in the last lesson or talked about in the last lesson, right? That number is going to help us get our kind of other markings on this graph. So I can add 0.025 3 times on the right. I can subtract 0.025 3 times on the left. And then this gives me an idea of what kind of proportions of Harley-Davidsons I could get in all these different samples. And then from there, I can take it one step further, use my normal model calculator that we've used for 2 units now. I can put in 0.14 is my mean, 0.025 is my standard deviation, plot distribution. There's all those numbers labeled. And then I can use that to find different probabilities. So what's the probability that a sample of 200 motorcycles would have 10% or less? So 10% or less. Remember, 10% we need to turn into a decimal for this. So 10 out of 100 is 0.1, and I want less. So I'm going to say to the left of 0.1, calculate area, gives me 0.0548, or 5.48%. What is the probability that a sample of 200 motorcycles would have more than 20%? So that's to the right. So again, 20% as a decimal would be 0.2 as a proportion. So that would be, and I want greater than or more than, so I'm going to do to the right of 0.2, calculate area. Be really careful in these. If they're asking about percentages, we need to turn it into a proportion. If you try to put 20 as in 20%, it's going to give you a really, really crazy number. We have to turn that into a proportion in order for it to give us the answer. So 0.2 is 20%. So that is our lesson for sampling distributions with proportions.